In 1609, Galileo Galilei raised a small telescope toward the Milky Way from Padua, in northern Italy. The instrument was crude by modern standards, with narrow glass lenses and a frustratingly small field of view. Yet what Galileo saw through it quietly changed humanity's relationship with the night sky. The pale band was not a celestial cloud. It was filled with stars. Thousands of points appeared where the naked eye had seen only a soft, milky glow. Galileo could not know their distances, ages, or true nature, but an ancient mystery had suddenly become something physical. The discovery was astonishing. Though the story had begun many thousands of years before his telescope touched the sky. Imagine yourself beneath a much older night. There are no cities glowing beyond the horizon, no aircraft crossing overhead, and no satellites silently sliding among the constellations. When darkness arrives, it arrives completely. You hear insects moving through grass and perhaps a fire settling behind you. Smoke carries the smell of wood into the cool air. Beneath your feet, the ground still holds a little warmth from the vanished sun. Above you stretches the Milky Way. Without artificial light, it looks considerably richer than it does from most modern cities. A broad, luminous band crosses the heavens, broken by dark patches and crowded with countless visible stars. You do not know that you are looking through a galaxy. You cannot know. For early humans, the sky was not a distant scientific laboratory separated from ordinary existence. It was a clock, calendar, compass, source of stories, and sometimes a warning. Long before written history, people noticed repeating patterns among the lights overhead. The sun moved predictably across the sky, while the moon changed shape through a familiar sequence. Certain stars returned with the seasons. Those repetitions mattered because survival depended on recognizing rhythms in the surrounding world. Migrating animals appeared at particular times, plants changed with seasons, and rainfall often followed recurring annual patterns. The sky offered another way to remember them. Archaeologists have discovered prehistoric structures whose orientations may correspond with important solar or lunar positions. Yet interpreting such remains requires caution because ancient builders rarely left explanations beside their stones. Researchers still debate how deliberately some prehistoric monuments encoded astronomical knowledge. Alignment can reflect careful observation, religious meaning, landscape features, coincidence, or several purposes working together. Stonehenge provides a famous example. Its surviving stones in southern Britain contain clear relationships with important solar directions, particularly around the solstices. Yet its builders probably understood the place through meanings far richer than a simple astronomical calendar. They were not standing around discussing astrophysics. Still, they watched carefully. Elsewhere, communities learned that certain stars could announce seasonal changes before those changes became obvious on Earth. Such observations accumulated slowly across generations and became woven into practical knowledge and cultural memory. The Milky Way itself invited another kind of attention. Unlike the sun or moon, it had no obvious solid shape. It looked like a luminous path poured across darkness, fading gradually along its edges. Different societies imagined it in remarkably different ways. It became a celestial river, a road, smoke, scattered grain, divine milk, or a pathway associated with ancestors. These interpretations varied enormously, and reducing them into one universal ancient belief would erase their richness. There is something understandable beneath that variety. You are looking upward without knowing what stars actually are. The glowing band appears permanent, enormous, unreachable, and strangely textured against the darker surrounding sky. Your senses provide almost no clue about distance. A bright planet may appear larger than a distant star, although the star itself can dwarf the planet. Two stars that seem close together might actually lie hundreds of light years apart. The heavens flatten immense depth into a shining surface. That illusion shaped early cosmologies to many ancient observers. The sky reasonably appeared like a great enclosing structure around the human world. Earth seemed stable beneath your feet, while everything overhead appeared to move. And experience supported that conclusion. You feel no planetary rotation. You hear no rushing sound as Earth travels through space, and nothing beneath you seems to race around the sun. Instead, sunrise arrives in the east. Stars sweep slowly overhead. The heavens appear to turn around you. From that evidence, placing Earth near the center of the cosmos was not foolish. It was an understandable interpretation of what human senses seem to demonstrate every day. Yet there was another clue hidden in the Milky Way. Its brightness was uneven. Some regions appeared thick with light, while others contained mysterious dark gaps. Today, you know that much of this darkness comes from enormous clouds of interstellar dust, blocking more distant stars. Early observers had no such explanation. They simply saw darkness inside light. On especially clear nights, the effect could be dramatic. The Milky Way divided and twisted overhead, particularly near the brighter regions visible toward the Galactic Center. There was something almost geographical about it. That appearance encouraged people to imagine paths and landscapes among the stars. Before anyone mapped the galaxy scientifically, humans had already mapped it culturally. One curious feature of ancient astronomy was how accurately people could observe without sophisticated instruments. Patient observers could track planetary movements, recognize eclipses, distinguish seasonal star patterns, and preserve knowledge across generations. The human eye became the first astronomical detector. Memory became the first archive. The horizon became the first measuring instrument. Yet the galaxy itself remained concealed by perspective. You lived inside it, which made understanding its shape extraordinarily difficult. Imagine standing deep inside a vast forest at night and attempting to determine the forest's complete shape. Trees surround you in every direction, while distance disappears into overlapping trunks. The Milky Way presents a similar problem. Most of its visible stars belong to the same immense structure containing the Sun, because you observe from within its disk. Distant stars overlap into the pale band crossing your sky. That explanation would require concepts unavailable to early humanity. Stars first needed to become physical objects rather than fixed lights. Their distances had to become imaginable, and Earth's position needed to lose its ancient privilege. Even the universe had to become larger. For now, none of that has happened. You remain beneath the ancient sky, feeling cool air against your skin, while firelight flickers behind you. Above, the galaxy continues its enormous rotation without announcing what it is. Its oldest stars are already ancient. Its spiral structure has been evolving for billions of years, while generations of stars have lived and disappeared before any human could name them. Somewhere inside those ancient stellar generations, heavier elements were forged and scattered through space. Much later, that recycled material would contribute to the formation of the Sun, Earth, and eventually your own body. You are therefore not merely observing the Milky Way. You are made from its history. But humanity does not understand that yet. For countless generations, people simply watch the luminous river overhead and remember when particular stars rise. Knowledge passes quietly from parent to child, navigator to traveler, farmer to farmer, and storyteller to listener. Eventually, observation becomes record-keeping. Marks become numbers. Patterns become tables. Predictions become increasingly precise. Along the great river valleys of the ancient world, professional sky watchers begin recording celestial movements with extraordinary patience. The mysterious heavens are about to become something that can be calculated. And once humans begin measuring the sky, the Milky Way's second history truly begins, the long story of a species slowly discovering the galaxy that had surrounded it all along. Thousands of years after people first learned the seasonal rhythms of the sky, another kind of observer began looking upward. This observer carried clay tablets, measuring tools, written records, and something even more powerful, accumulated memory. You can imagine yourself entering ancient Babylon after sunset. The heat of the day still lingers in mud brick walls, while cooler air settles across the Euphrates plain. Oil lamps flicker in courtyards, carrying the faint smell of smoke and sesame oil. Above the city, the heavens remain brilliantly dark. There are no electric lights to soften the stars. Jupiter can shine like a steady lantern, while Venus sometimes dominates the horizon with startling brightness. Babylonian scholars watch these wandering lights with extraordinary persistence. By the first millennium BC, they were recording celestial events systematically on clay tablets. They tracked lunar phases, eclipses, planetary appearances, and the positions of important stars. This was more than casual stargazing. Generation after generation added observations to an expanding archive, allowing patterns to emerge across periods longer than any individual lifetime. One remarkable achievement involved eclipses. Babylonian astronomers recognized recurring relationships that allowed some lunar eclipses to be anticipated. Their predictions were not based on modern gravitational theory, but repeated observations could still reveal reliable cycles. The sky was becoming predictable. That change was profound. A celestial event that once seemed sudden could now sometimes be expected through mathematics and careful record-keeping. Yet Babylonian astronomy remained intertwined with religion, kingship, and divination. Unusual celestial events could be interpreted as signs concerning rulers, kingdoms, harvests, or approaching troubles. To modern ears, astronomy and omen reading may sound like uncomfortable companions in their world. However, separating them would have seemed rather artificial. Observation served many purposes at once. A curious Babylonian practice involved maintaining long collections of celestial omens. Scholars attempted to connect events in the heavens with events below, creating enormous traditions of interpretation. The predictions were not scientific in the modern sense. The observations supporting them could nevertheless be exceptionally careful. That combination reminds you that accurate measurement does not automatically produce accurate explanations. Humans often learn how something behaves before understanding why it behaves that way. Farther west, Egyptian observers developed their own relationships with the heavens. Stand beside the Nile before sunrise, and the atmosphere feels entirely different. The air may carry damp earth from the river, mingled with dust and vegetation along the banks. For agricultural communities, timing mattered enormously. The Nile's annual flooding shaped farming, taxation, food storage, and the rhythm of ordinary life. Egyptian calendars therefore became closely connected with celestial cycles and seasonal changes. The rising of Sirius became especially significant. Its annual appearance near dawn occurred close to the season associated with the Nile's inundation. Although the relationship changed gradually over long periods, priests and officials watched the sky carefully. Stars also became connected with religious ideas, temple orientations, timekeeping, and the journey through night. Some Egyptian systems divided darkness using groups of stars that appeared successively. You might think of them as celestial time markers. At night, without a mechanical clock beside your bed, the changing sky itself can tell you that hours have passed. Exactly how particular Egyptian monuments were designed in relation to astronomical observations remains debated. Scholars continue examining alignments, texts, architecture, and changing stellar positions across centuries. The evidence is fascinating, but rarely simple. Ancient people did not divide religion, architecture, administration, and astronomy into the neat categories used by modern textbooks. Meanwhile, across the Mediterranean world, Greek thinkers began asking a somewhat different question. Could the heavens be explained geometrically? You now find yourself standing near the Aegean beneath a clear evening sky. Waves move gently against stone, carrying the smell of salt through warm air. The same Milky Way stretches overhead, but the intellectual tools used to interpret it are changing. Greek philosophers inherited knowledge from older civilizations while developing competing models of nature. They debated Earth's shape, celestial motion, planetary behavior, and the structure of the cosmos. By the classical period, educated thinkers increasingly accepted that Earth was spherical. Evidence could be gathered from ordinary experience. During lunar eclipses, Earth's shadow cast upon the moon appeared curved. Travelers moving north or south noticed that familiar stars changed their heights above the horizon. Ships also disappeared gradually beyond the sea. These observations helped turn the shape of Earth into a question that geometry could address. Aristotle later described arguments for a spherical Earth while presenting a cosmos centered upon it. In his model, Earth rested near the middle, while celestial bodies moved around it. Again, this arrangement matched everyday appearances remarkably well. You stand still. The sky moves, without instruments capable of detecting Earth's motion. Placing the stationary world at the center seemed entirely reasonable, yet Greek astronomy also produced alternatives. In the 3rd century BC, Aristarchus of Samos proposed that Earth rotated and traveled around the Sun. Only fragments of his astronomical thinking survive, leaving historians uncertain about some details of his reasoning. His idea did not become dominant. One difficulty was observational. If Earth moved around the Sun, nearby stars should appear to shift slightly against more distant stars during the year. This effect, called stellar parallax, exists. Ancient instruments could not detect it. Without measurable parallax, a moving Earth required stars to be unimaginably distant. That possibility was difficult to establish with the evidence available. The Earth-centered model therefore survived partly because it worked. Meanwhile, Hipparchus brought extraordinary precision to stellar astronomy during the 2nd century BC. He compiled a catalogue containing positions and brightness estimates for hundreds of stars. He also discovered something wonderfully subtle. By comparing observations across generations, Hipparchus recognized that the celestial coordinate system slowly shifts over centuries. Today, this motion is understood as the precession of Earth's rotational axis. The sky itself seemed to change, very slowly. You would never notice precession during a single night, or even across one human lifetime. Only preserved observations made such a discovery possible. This was the quiet power of astronomical records. Humans were beginning to extend their senses through time. Still, the Milky Way remained mysterious. Some Greek thinkers speculated about its nature, offering explanations involving celestial fire, atmospheric effects, or concentrated starlight. Aristotle associated it with processes occurring below the lunar realm rather than distant stars. Others suspected something more stellar. The evidence remained insufficient. To your naked eye, the luminous band refuses to separate completely into individual points. It resembles mist, yet behaves like a permanent feature of the heavens. There is no telescope to settle the matter, so you measure what you can. You record where stars appear. You follow planets against constellations. You compare eclipses, seasons, and rising points along the horizon. Slowly, the heavens become coordinates. The galaxy still hides its enormous architecture, but humanity has acquired something essential for eventually revealing it. The sky has become measurable, and once positions can be measured, models can be tested, corrected, and passed forward. Soon, those measurements will be gathered into one of antiquity's most influential mathematical pictures of the cosmos. For many centuries afterward, almost every serious astronomer around the Mediterranean world will have to reckon with it. By the 2nd century AD, generations of astronomers had turned the night sky into an increasingly ordered landscape. Stars possessed positions, planets followed recognizable paths, and eclipses could sometimes be anticipated with impressive accuracy. Yet one problem remained stubbornly beautiful. The planets wandered. You can see the difficulty yourself from an ancient Mediterranean rooftop. Evening warmth rises gently from stone beneath your feet, while cooking fires leave traces of smoke and herbs in the air. Most stars maintain familiar patterns as the months pass. Mars does something stranger, night after night. It usually drifts gradually against the distant stars. Then, during certain periods, it seems to slow, stop, reverse direction, and eventually resume its original path. Today, you know why. Earth and Mars travel around the Sun at different speeds, so Earth's changing viewpoint creates the apparent backward motion called retrograde motion. Ancient observers did not possess that explanation. They possessed measurements, and measurements demanded a model. Around AD 150, Claudius Ptolemy produced the most influential mathematical synthesis of ancient astronomy, working in Alexandria. He drew heavily upon earlier Greek and Babylonian traditions, especially observations associated with Hipparchus. His great astronomical work described a geocentric cosmos. Earth rested near the center. The moon, sun, planets, and stars moved around it according to mathematical combinations of circular motions. The system was more sophisticated than the simple picture sometimes presented today. Planets did not merely travel around Earth on single perfect circles. Ptolemy used smaller circles moving upon larger ones. These smaller motions, commonly called epicycles, helped reproduce the complicated wandering of planets across the sky. He also used mathematical devices that improved predictions further. To someone observing without telescopes, the system could work remarkably well. That practical success matters because historical ideas should be judged against the evidence available to their creators. Ptolemy was not refusing an obvious modern truth. The obvious evidence seemed to favor him. Stand outside and feel the ground beneath your sandals. Earth does not appear to rotate at tremendous speed. There is no constant gale produced by planetary motion. Dropped objects fall almost straight downward, rather than being mysteriously left behind as the surface races eastward. Meanwhile, the sun clearly crosses the sky. From ordinary experience, a stationary Earth feels natural. There was also the unresolved problem of stellar parallax. If Earth orbited the sun, nearby stars should shift against more distant ones during different seasons. Ancient astronomers detected no such shift. The actual reason is almost comical in its scale. The stars are simply much farther away than they could reasonably imagine. Even the nearest star beyond the sun is so distant that its parallax is tiny. Measuring it would require instruments far more precise than anything available in antiquity. The universe was hiding its true arrangement behind its enormous size. Ptolemy's system therefore became useful because it predicted celestial positions while fitting broader philosophical ideas about cosmic order. It was not perfect. Astronomers could refine parameters as observations improved, and different mathematical traditions handled particular problems in different ways. Still, the framework endured. One quirky feature of ancient and medieval planetary modeling is the sheer ingenuity required to preserve circular motion. Circles carried deep philosophical appeal because they represented regularity and perfection. Nature, unfortunately, had not signed that agreement. Planetary motion would eventually prove elliptical. For now, circles ruled the heavens. Beyond the planets lay the sphere of fixed stars in traditional cosmological pictures. Constellations seemed attached to this distant celestial region, rotating together around Earth. And across those stars stretched the Milky Way. Its nature remained unsettled. Some ancient philosophers placed the phenomenon relatively close to Earth. Others imagined that countless stars might contribute to its pale brightness. Without magnification, neither possibility could be decisively demonstrated. You might spend an entire lifetime beneath clear skies and never see enough detail to settle the argument. This uncertainty reveals an important boundary in ancient astronomy. Mathematics had become powerful enough to predict movements, but instruments had not yet become powerful enough to reveal the physical nature of most celestial objects. Astronomers knew where many stars were. They did not know what stars were. They could calculate planetary positions without knowing that planets were worlds. They could describe the Milky Way's path without knowing that humanity lived inside it. The cosmos was becoming mathematically precise while remaining physically mysterious. Ptolemy also preserved a substantial star catalogue within his astronomical work. It listed more than 1,000 stars, organized into constellations familiar to Mediterranean astronomy. You can imagine copying such information by hand. There are no printing presses. Every table, diagram, number, and explanatory sentence must survive through manuscripts reproduced by individual scribes. Ink carries its faint mineral smell. Papyrus or parchment feels slightly rough beneath your fingers. A copying mistake can travel surprisingly far, yet knowledge survives. Ptolemy's astronomy would move across languages, religions, dynasties, and continents. Scholars would study it, criticize it, correct it, and develop alternatives to its mechanisms. Historians still debate exactly how observations attributed to Ptolemy were obtained and how extensively he relied upon earlier data. Such questions remain part of understanding how ancient astronomical knowledge was assembled. What matters for your journey is its extraordinary longevity. For more than a millennium, geocentric astronomy remained intellectually powerful because it combined mathematics, inherited physics, philosophical expectations, and observational usefulness. Then the political world surrounding Mediterranean scholarship changed dramatically. The Western Roman Empire fragmented. Libraries disappeared in some places while surviving or developing elsewhere. Astronomical knowledge did not simply vanish, it traveled. Manuscripts moved through the Byzantine world, Persian intellectual traditions, Syriac scholarship, and eventually the rapidly expanding centers of learning under Islamic civilization. There, astronomers did more than preserve ancient texts. They measured again. That distinction is essential. Imagine the Milky Way above Baghdad, centuries later, shining through dry night air while scholars compare inherited tables against actual planetary positions. Numbers do not always agree. Old models need adjustments. New instruments become larger and more precise. Observatories emerge where teams can watch the heavens systematically. The ancient cosmos is still standing, but small cracks are appearing inside its mathematical machinery. Those cracks will matter. For now, you leave Alexandria with a universe arranged around Earth, its stars apparently fixed upon a distant celestial sphere. The Milky Way remains a pale, unresolved ribbon beyond explanation. Humanity has learned to calculate the heavens with astonishing skill. The next step will be more dangerous for old assumptions. Someone must begin asking whether the calculations describe reality itself, or merely provide an elegant way of predicting what appears in the sky. Centuries pass, kingdoms change, and the Milky Way continues crossing the night exactly as before. The stars seem indifferent to languages, borders, dynasties, and the rise and disappearance of cities beneath them. By the 8th century, new centers of scholarship were flourishing across the Islamic world. Imagine yourself in Baghdad on a clear night. The day's heat has faded from the streets, leaving warm stone beneath your feet. Somewhere nearby, water moves softly through a courtyard fountain. You smell lamp oil, dust, paper, and cooling earth. Above the rooftops, The familiar stars shine without modern light pollution. The Milky Way stretches across the darkness like a pale road whose true distance remains completely unknown. Scholars here inherit an enormous intellectual landscape. Greek astronomical works are translated, studied, compared, and debated alongside traditions from Persia and India. Ptolemy's mathematical astronomy becomes especially influential. But inheritance does not mean obedience. Astronomers examine the old numbers against the sky. Sometimes they disagree. One important figure was al-Battani, who worked during the 9th and early 10th centuries. Through careful observations, he improved measurements involving the solar year, planetary motions, and the changing positions of celestial objects. His work demonstrates a central habit of astronomy. Measure again. Even a respected authority cannot make Mars appear somewhere it does not actually appear. Other astronomers refined star positions and investigated apparent stellar brightness. Improved mathematical methods allowed calculations to become more reliable. The heavens were increasingly treated as a system open to correction. During the 10th century, Abd al-Rahman al-Sufi produced an influential description of the fixed stars. He compared inherited stellar information with his own observations and described brightnesses and positions. His work included something particularly interesting for your galactic journey. He recorded a faint cloudy object in the constellation Andromeda. Today you recognize that glow as the Andromeda Galaxy. To the naked eye, under dark conditions, it looks like little more than a dim smudge. There is no obvious reason to imagine hundreds of billions of distant stars inside it. The light reaches your eye quietly. Its meaning does not. The Andromeda Galaxy is roughly 2.5 million light-years away. The photons entering an ancient observer's eyes therefore began traveling toward Earth long before modern humans existed. No medieval astronomer could have known this. The faint patch was simply another mysterious object in a sky already full of mysteries. That is one of astronomy's gentler ironies. Humanity could see another major galaxy long before anyone understood that the Milky Way itself was a galaxy. Observational astronomy also became increasingly dependent on instruments. The astrolabe, developed from earlier traditions and greatly refined and widely used in Islamic societies, could help determine celestial positions, local time, and other astronomical quantities. Hold one in your hands. Metal feels cool against your fingers. Carefully engraved lines divide the instrument into a miniature mathematical representation of the heavens. It is elegant and practical, yet the astrolabe does not magnify stars. The naked eye remains the detector. The improvement lies in measurement. Large observational instruments eventually pushed precision further. Quadrants, armillary devices, and enormous fixed instruments allowed astronomers to measure angles more accurately than handheld tools permitted. The size of some later observatories could be astonishing. At Moraga, in the 13th century, astronomers worked within a major observatory established under the patronage of Hulagu Khan. Nasir al-Din al-Tusi became closely associated with this institution. He and other scholars developed mathematical devices capable of producing motions useful for modifying planetary models. One famous construction later became known as the Tusi couple. It generated linear oscillation from combinations of circular motion. That may sound abstract during a sleepy evening. Its importance was considerable. Astronomers were finding sophisticated ways to challenge troublesome features within Ptolemaic planetary theory while still working inside broadly geocentric frameworks. Farther east, another extraordinary observatory appeared at Samarkand during the 15th century. Ulugh Beg, ruler and astronomer, sponsored a massive observational program there. A huge meridian instrument allowed remarkably precise measurements of stellar positions. Imagine entering that observatory at night. Voices remain low. Cold air settles over masonry, while assistants prepare records and compare measurements under lamplight. The work demands patience. A star crosses a chosen position only when the heavens permit it. There is no button to press and no automated telescope following the target. You wait, then you measure. Ulugh Beg's star catalogue contained positions for roughly 1,000 stars and represented one of the finest achievements of pre-telescopic observational astronomy. Its precision emerged from geometry, engineering, repetition, and disciplined eyesight. Meanwhile, scholars continued questioning aspects of inherited cosmology. Ibn al-Haytham criticized parts of Ptolemy's astronomical framework because mathematical devices should correspond to plausible physical motions. This distinction mattered. A model might predict a planet's location while still giving an unsatisfactory account of what physically exists. Astronomers increasingly confronted that tension. Researchers continue discussing how particular mathematical developments in Islamic astronomy influenced later European thinkers. Similar mathematical constructions appear in later works, including those associated with Copernicus, but exact routes of transmission remain uncertain. Ideas rarely travel with convenient labels attached. Manuscripts move. Scholars travel. Concepts are translated, adapted, forgotten, and rediscovered. The history of astronomy is less like a straight road and more like starlight passing through many pieces of glass. Throughout these centuries, ordinary people still experience the heavens directly. A merchant crossing desert country can use stars for direction. A farmer recognizes seasonal changes in familiar constellations. Travelers watch the moon. Sailors learn celestial patterns above open water. The Milky Way remains especially impressive from landscapes without artificial illumination. Its dark lanes can appear almost as prominent as its brighter regions. No one yet understands those dark structures as enormous concentrations of dust. Nor does anyone know that the Milky Way contains a central bulge, spiral structure, a stellar halo, and vast quantities of invisible matter. Human knowledge remains limited by available instruments, but those instruments are becoming better. More importantly, the habit of testing inherited claims against observation is becoming deeply established. By the late medieval period, astronomical traditions across Europe are also changing. Translations make ancient and Islamic astronomical works increasingly accessible to Latin scholars. Universities develop. Printing will soon accelerate the movement of ideas. Navigation creates growing demand for reliable astronomical tables, while calendar problems encourage further attention to celestial motion. The old Earth-centered cosmos still dominates. It remains useful, familiar, and supported by centuries of scholarship. Yet its machinery has become complicated. Corrections accumulate, questions persist, and above every debate, the Milky Way continues glowing without revealing whether it belongs to the atmosphere, the distant stars, or something stranger. Soon, a quiet scholar in Renaissance Europe will rearrange the planets around the Sun. His proposal will not immediately explain the galaxy, but it will loosen humanity's position at the center of everything. Once Earth begins to move, the universe can begin expanding in the human imagination. By the early 16th century, the old Earth-centered cosmos had survived for more than 1,000 years. It had been questioned, adjusted, translated, refined, and repeatedly compared against observations. Then Nicholas Copernicus quietly moved Earth. You can imagine yourself in Frombork, on the Baltic coast, during a cold evening in the early 1500s. Wind presses against stone walls, carrying the smell of damp earth and distant sea water. The stars above look completely ordinary. That is precisely the problem. Nothing in the night sky announces that Earth is moving around the sun. Beneath your feet, the ground feels reassuringly stationary. Copernicus nevertheless explored a sun-centered arrangement. In his mature model, Earth rotated daily and traveled around the Sun yearly. The other known planets also orbited the Sun, while the Moon continued circling Earth. This rearrangement explained some celestial patterns elegantly. Retrograde motion no longer required planets to physically reverse their journeys around Earth. It could emerge naturally from the changing viewpoints of planets moving at different speeds. Mars only appeared to wander backward. Earth was overtaking it. Yet Copernicus did not simply sweep away the mathematical complexity of earlier astronomy. He remained committed to combinations of uniform, circular motions and still required elaborate geometrical constructions. The revolution began rather quietly. His major work appeared in 1543, near the end of his life. The heliocentric model offered a new arrangement, but decisive observational proof remained unavailable. Stellar parallax was still missing. If Earth crossed a vast orbit each year, why did the stars maintain apparently fixed positions? Copernicus had an answer. The stars were extremely distant. That solution worked mathematically, but it enlarged the cosmos dramatically. Humanity had to accept that the stellar realm might lie far beyond traditional expectations. Many scholars hesitated. Their caution was not merely stubbornness. A moving Earth created difficult questions about physics, motion, falling objects, and the apparent stability of the world. A new cosmology needed more than attractive planetary diagrams. Then another observer transformed the quality of astronomical evidence. Tycho Brahe watched the heavens with an almost obsessive precision. In 1572, a brilliant new star appeared in the constellation Cassiopeia. Today, you know it as a supernova, the explosion of a star whose light suddenly became visible across enormous distances. Tycho measured it carefully. The object showed no detectable daily parallax, suggesting atmospheric proximity. It therefore appeared to belong among the distant stars. The supposedly unchanging heavens had changed. A comet in 1577 caused further trouble. Tycho's measurements indicated that it traveled beyond the moon, contradicting traditional ideas that celestial regions consisted of solid nested spheres carrying the planets. The ancient cosmic architecture was beginning to crack. Tycho still rejected Earth's annual motion and developed a hybrid system. In his arrangement, the Sun orbited Earth while the other planets orbited the Sun. It was clever. It also matched many observations. This period was not a simple contest between intelligent heliocentrists and foolish geocentrists. Several models competed because the available evidence allowed genuine uncertainty. Scholars still debate the relative importance of philosophical, religious, mathematical, and observational considerations in individual astronomers' choices. Then came Johannes Kepler. Kepler inherited Tycho's extraordinarily precise planetary observations, particularly measurements of Mars. He tried repeatedly to fit them into combinations of circular motions. Mars refused to cooperate. The disagreement was small. Small was enough. Kepler eventually abandoned perfect circles and concluded that planets travel along ellipses with the Sun at one focus. This was an enormous conceptual surrender. For centuries, circular motion had seemed naturally suited to celestial perfection. Kepler allowed observation to defeat aesthetic expectation. His planetary laws revealed mathematical relationships between orbital shapes, speeds, and periods. The heavens became less geometrically perfect. They became more accurate. Then, in 1609, a new instrument entered the story. Galileo Galilei heard reports of a Dutch device that made distant objects appear closer. He constructed improved versions and pointed them upward. Imagine standing beside him. The telescope is narrow and awkward. Your eye must remain carefully positioned, and the image is nothing like a modern observatory photograph. Still, the moon suddenly has mountains. Its surface contains shadows, irregularities, and landscapes. The heavens are no longer perfectly smooth. Galileo turns toward Jupiter. Small points of light appear beside it. Over successive nights, their positions change. Galileo realizes that these objects orbit Jupiter. Not everything circles Earth. Then Venus reveals phases resembling those of the moon. The full sequence fits naturally if Venus travels around the Sun. The older Ptolemaic arrangement cannot easily survive that evidence in its traditional form. Yet for the history of the Milky Way, another observation matters even more. Galileo points his telescope toward the pale band crossing the sky. The cloudy glow breaks apart. Stars appear everywhere. Some are bright enough to see individually without magnification. Many others had remained hidden because their combined light blurred into a luminous haze. The Milky Way is not atmospheric smoke. It is deeply connected with stars. For perhaps the first time, an instrument reveals something about the galaxy's physical nature that naked eyes could never resolve. The experience must have been strange. You move the telescope slightly and discover more stars. Then more. Darkness that seemed nearly empty becomes crowded. The universe appears to gain population whenever the instrument improves. This pattern will repeat for centuries. Larger telescopes will reveal fainter stars. Photography will reveal objects too dim for eyes. Radio receivers will uncover structures hidden by dust. Space telescopes will detect wavelengths blocked by Earth's atmosphere. Every technological improvement will enlarge the known Milky Way. But Galileo cannot yet measure the distances to those countless stars. He does not know whether the Milky Way forms a disk, sphere, ring, or something else entirely. The telescope has solved one mystery while creating many more. You step away from the eyepiece. Cool night air touches your face. Somewhere nearby, wood burns in a hearth, and the instrument's metal feels cold beneath your fingers. Above you, the Milky Way still resembles the same pale river known to prehistoric observers. But intellectually, everything has changed. Earth can move. Planets can circle something other than Earth. Celestial objects can change. The moon can possess mountains, and the Milky Way can dissolve into innumerable stars. Humanity has finally begun opening the galaxy with glass. The next question is unavoidable. What force keeps this moving universe together by the late 17th century? The heavens had become a place of moving worlds rather than perfect celestial machinery. Kepler had described how planets traveled, while Galileo had revealed landscapes and moons invisible to ordinary sight. But another question remained. Why did any of it move this way? You can imagine yourself in England during the 1660s, walking beneath an evening sky after rain. Wet grass brushes your shoes, and the air carries the smell of damp soil and wood smoke. Above you, the moon follows its familiar path. An apple falls toward the ground. The famous story connecting Isaac Newton with a falling apple has been polished by centuries of retelling. Newton himself later recalled that falling fruit helped provoke thoughts about gravity. The important insight was larger than the fruit. Perhaps the force pulling an object toward Earth also reached the moon. Newton developed this possibility into a mathematical description of universal gravitation. In 1687, his great work on motion and gravity presented a universe governed by principles applying both on Earth and in the heavens. The old division weakened dramatically. Celestial objects did not require entirely separate rules. The same gravity affecting your body could guide planets around the Sun and the Moon around Earth. Kepler's elliptical orbits now gained a physical explanation. Gravity decreases with distance according to a precise mathematical relationship, combined with laws of motion. It explains why an orbiting body continually falls without simply crashing downward. You can picture an orbit as an endless fall. The moon falls toward Earth while moving sideways quickly enough to keep missing it. That sounds almost mischievous, yet the mathematics works beautifully. Newton's framework transformed astronomy because celestial motions could now be understood as consequences of physical forces rather than purely geometrical patterns. It also invited a much larger question. If gravity acts universally, stars should influence other stars. The Milky Way could therefore be a physical system rather than a decorative background. Still, nobody knew its shape. Galileo's telescope had revealed that the luminous band contained enormous numbers of faint stars, but without reliable stellar distances. Determining their arrangement remained extraordinarily difficult. The problem is easier to feel than explain. Imagine standing inside a foggy forest at night. You count visible trees in different directions, but nearby trees appear larger and clearer than distant ones. Fog hides some completely. Now replace trees with stars. Brightness becomes an unreliable guide because stars themselves differ enormously in luminosity. A faint nearby star can resemble a brilliant distant one. Distance remains hidden. Astronomers therefore improved their telescopes. Early refracting telescopes suffered badly from colored fringes and blurred images because lenses bend different colors by slightly different amounts. One response was simply to build longer instruments. Some became absurdly long. 17th century astronomers experimented with telescopes extending many meters, occasionally dispensing with ordinary tubes and mounting separated optical components on elaborate structures. Operating them could be frustrating. Wind shook equipment, alignment wandered, cold fingers made adjustments unpleasant. Astronomical progress has always contained more inconvenience than romantic paintings suggest. Then reflecting telescopes offered another approach. Newton constructed a practical reflecting telescope using a curved mirror rather than relying entirely on a large objective lens. Mirrors reduced certain optical problems. Over later centuries, this basic principle would allow astronomers to construct increasingly enormous light-gathering instruments. More collected light meant fainter objects. Fainter objects meant deeper space. The Milky Way slowly became crowded with objects previously hidden from human vision. Astronomers catalogued stars, clusters, and mysterious fuzzy patches called nebulae. Some nebulae looked cloudy, while others appeared increasingly stellar under stronger magnification. Their nature remained uncertain. Were they nearby clouds, unresolved star systems, perhaps distant structures? The evidence could not yet decide. During the 18th century, thinkers began speculating more boldly about the Milky Way's architecture. In 1750, Thomas Wright proposed that the appearance of the Milky Way could result from our location inside an enormous flattened arrangement of stars. The exact details of his cosmology were unusual and intertwined with theological ideas. Still, the basic geometric insight was powerful. A flattened stellar system could appear as a bright band from within. Imagine standing inside a thin disk filled with lamps. Look along the plane, and your gaze passes through many lamps. Look upward away from the plane, and you see fewer. The sky would appear brighter in a band. That is broadly what happens in the Milky Way. Immanuel Kant soon developed related ideas and suggested that some faint nebulae might be distant stellar systems comparable to the Milky Way. He called them island universes. It was a magnificent possibility. It was also largely speculative. No telescope of the period could demonstrate that the Andromeda Nebula lay millions of light-years beyond the Milky Way. Historians continue discussing how much these 18th-century speculative models anticipated modern galactic astronomy. Their language sometimes sounds surprisingly modern, while their physical assumptions could differ greatly from today's understanding. Still, humanity's imagination was expanding. The Milky Way was becoming something with structure. The next challenge was to measure that structure. For this, astronomy needed observers willing to count enormous numbers of stars across different regions of the sky. William Herschel would become one of them. Before Herschel, however, another useful astronomical habit was developing through cataloging. Charles Messier spent years searching for comets. Unfortunately for him, the sky contained fuzzy objects that looked annoyingly comet-like but refused to move, so he catalogued them. His list eventually included star clusters, nebulae, and galaxies, although those categories were not yet fully understood. It was essentially a list of celestial objects that could waste a comet hunter's time. A practical nuisance became an astronomical treasure. Among these objects were globular clusters, dense spherical gatherings containing enormous populations of old stars. Later, their distribution would help astronomers locate the Milky Way's center, but that discovery remained far ahead. For now, step outside beneath the 18th century sky. The Milky Way still looks soft to your unaided eyes. Through telescopes, however, it becomes a landscape containing stars, clusters, dark gaps, and unresolved clouds. Gravity has united terrestrial and celestial physics. Telescopes are gathering more light. Mathematics can predict planetary motion with extraordinary accuracy. Yet humanity still cannot answer a seemingly simple question. Where are we inside the stars? Soon, William Herschel will attempt an answer by turning his telescope across the entire sky and counting. The resulting map will be wrong in important ways. It will also represent one of the first serious attempts to draw our galactic home from the inside. By the late 18th century, the Milky Way had become more than a glowing mystery. Galileo had resolved its light into stars, while thinkers such as Thomas Wright imagined those stars arranged within an enormous flattened system. Someone now had to measure it. In 1781, William Herschel was observing from his garden in Bath, England, when he noticed an unusual object among the stars. At first, he suspected that he had found a comet. It was Uranus. The discovery made Herschel famous, but his deeper ambition stretched far beyond adding another planet to the solar system. He wanted to investigate the structure of the heavens themselves. Imagine joining him during a cold observing night. The garden is dark and damp. Metal fittings feel painfully cold beneath your fingers, while the smell of wet grass mixes with smoke drifting from nearby chimneys. Beside the telescope stands William's sister, Caroline Herschel. She is not merely watching. Caroline records observations, performs calculations, prepares catalogues, and conducts her own searches. She discovers several comets and becomes an important astronomer in her own right. The siblings work through long nights. William observes. Caroline writes, "Numbers accumulate. Their telescopes are increasingly powerful reflecting instruments." And William becomes exceptionally skilled at constructing mirrors capable of gathering more light. Eventually, he builds a reflector with a mirror roughly 48 inches across. The instrument is enormous for its era. Visitors come to see it. King George III supports Herschel's astronomical work, allowing him to devote far more time to observing than most independent astronomers could afford. Yet his most influential galactic investigation uses a deceptively simple method: count stars. Herschel divides the sky into many directions and observes selected fields through his telescope. He counts how many stars appear within each field. The reasoning seems elegant. If stars are distributed relatively evenly through space, directions containing more stars should extend farther through the Milky Way. Directions containing fewer stars should reach its edge sooner. Imagine standing inside a forest again. If trees have roughly similar spacing, you might estimate the forest's shape by counting how many trunks lie along different lines of sight. Herschel attempts something comparable with stars. The work is patient and repetitive. You aim, you count, you record, then you move slightly and begin again. There are no digital detectors automatically identifying points of light. Each field passes through a human eye and becomes handwritten data. From these observations, Herschel constructs a map. His Milky Way resembles an irregular flattened structure, somewhat like a rough disk with branching extensions. The Sun appears relatively close to the middle. For its time, the achievement is extraordinary. Humanity has attempted to map the galaxy from inside it. Unfortunately, the method contains hidden assumptions. Herschel effectively needs his telescope to see through the entire stellar system in each direction. He also needs the stars he counts to provide a reasonably representative picture of spatial distribution. Neither condition is fully satisfied. Interstellar dust creates the greatest problem. The Milky Way contains enormous clouds of tiny solid particles that absorb and scatter visible light. Look toward heavily obscured regions, and distant stars disappear behind dark material. Herschel does not know this. To him, a region with fewer visible stars can appear to represent the galaxy's edge. In reality, the galaxy continues beyond the curtain. This creates one of astronomy's recurring traps. Not seeing something is not the same as proving that nothing is there. Dust would confuse attempts to map the Milky Way for generations. The problem is particularly severe toward the Galactic Center, where dense material blocks much of the visible light arriving from distant stars. The true center lies roughly 26,000 light-years from the Sun. Herschel has no way to measure such a distance. Reliable stellar distances remain one of astronomy's greatest missing tools. Even the nearest stars are so remote that their annual parallax is extremely small. Astronomers repeatedly attempt to detect this shift, but instruments struggle to provide trustworthy measurements. Some apparent detections prove mistaken. The stars continue guarding their distances. Herschel therefore estimates structure mainly from brightness and star counts. His map is imperfect, yet it changes the question. The Milky Way now has geography. It can possess edges, thickness, concentrations, and perhaps a center. Herschel also studies nebulae extensively. At first, he often suspects that sufficient telescope power might resolve many cloudy objects into stars. Some do resolve, others refuse. As his observations accumulate, Herschel gradually becomes more open to the possibility that genuine luminous nebulous material exists in space. This change is important. The heavens contain more than stars. Caroline contributes significantly to this cataloging work, helping organize observations that would influence later astronomical catalogues. A particularly curious object attracts William's attention in 1785. It is a faint nebula later known as NGC 1514. Herschel sees a central star apparently surrounded by luminous material. Such observations encourage him to consider nebulae as real physical structures rather than merely unresolved star clusters. Astronomy is beginning to discover interstellar space. It is not empty. Herschel also studies double stars, pairs that appear close together in the sky. Some turn out to be genuine physical systems whose stars orbit one another. This provides another triumph for Newtonian gravity. Gravity operates between stars. The law connecting apples, moons, and planets reaches into stellar systems. Meanwhile, Herschel's observations reveal immense numbers of faint stars beyond naked eye visibility. Each improvement in telescope power seems to expose another layer. The galaxy feels deeper, but how deep? That remains uncertain. Astronomers still argue about the nature of nebulae and the scale of the stellar system. Some speculate that distant cloudy objects could be separate island universes. Others place them within the Milky Way. There is not yet enough evidence to settle the matter. Scholars today also debate how closely Herschel's changing ideas correspond to later concepts of galactic evolution. His views developed across decades and should not be compressed into a single modern interpretation. Still, he accomplished something fundamental. He treated the Milky Way as an object that could be surveyed. You can almost feel the intellectual shift while standing beside his telescope. The galaxy is no longer merely the pale road overhead. It is a three-dimensional population of stars whose hidden architecture might be reconstructed through observation. Yet sight alone has reached another limit. A star remains only a point. Even Herschel's telescopes cannot show its surface. They cannot reveal what it contains, how hot it is, or why one star looks red while another appears blue-white. To understand the Milky Way properly, astronomers must learn what its stars actually are. The answer will come from something humans have been receiving since the first eyes turned upward: starlight. Instead of merely counting that light, 19th-century astronomers will begin breaking it apart. Inside those thin colored bands, the stars will finally reveal their chemistry. By the early 19th century, astronomers could map stars more carefully than William Herschel ever could. Yet every star still arrived at the telescope as a distant point of light. Then astronomers began opening that light. Imagine yourself in 1814, beside Joseph von Fraunhofer in Bavaria, examining sunlight spread through a glass prism. A narrow beam enters the instrument, and a delicate rainbow appears before you. The room smells faintly of glasswork, oil, and heated metal. You lean closer. The rainbow is not continuous. Hundreds of dark lines interrupt its colors, as though someone had drawn fine shadows across the spectrum. Fraunhofer carefully maps many of them. He does not yet possess the complete explanation, but those lines will become one of astronomy's most powerful tools. Light carries information. Several decades later, laboratory experiments by Gustav Kirchhoff and Robert Bunsen help reveal what the spectral lines mean. Heated chemical elements produce characteristic patterns of bright lines. Cooler gases can absorb those same wavelengths. Suddenly, astronomers possess something extraordinary. They can identify substances without touching them. You cannot collect a bottle of material from the sun, but sunlight can tell you that familiar elements exist there. The stars become accessible laboratories. Astronomers begin directing spectroscopes toward them. Hydrogen leaves recognizable signatures. Sodium, calcium, iron, and other elements announce themselves through distinctive patterns. The ancient belief that the heavens might be made from fundamentally different substances becomes increasingly difficult to maintain. Stars contain familiar matter. This realization quietly connects the Milky Way with Earth. The iron in tools and the calcium in your body are not ingredients confined to one small planet. The same kinds of atoms exist across enormous distances. One particularly charming twist arrives with helium. During observations of the Sun in 1868, astronomers detect a spectral signature associated with an unknown element. Helium is identified in the Sun before it is isolated on Earth. For once, humanity discovers part of terrestrial chemistry by looking into space. Spectroscopy also reveals motion. When a source moves toward you, its spectral features shift slightly toward shorter wavelengths. When it moves away, those features shift toward longer wavelengths. This Doppler effect turns light into a speed detector. A star can remain an unresolved point and still reveal movement along your line of sight. The Milky Way is becoming dynamic. Its stars are not pinned to a celestial shell. They move through space, orbit companions, approach the Sun, and recede from it. Astronomers also improve another essential measurement: distance. In 1838, Friedrich Bessel successfully measures the stellar parallax of 61 Cygni. The apparent shift is tiny, but it finally provides a convincing geometric distance to another star. The old objection to Earth's motion disappears. Stellar parallax had been missing not because Earth remained stationary, but because the stars were astonishingly distant. You can imagine the emotional scale of that measurement. Earth travels from one side of its orbit to the other, creating a baseline almost 300 million kilometers wide. Even with that enormous separation, nearby stars barely seem to move. Space is simply that large. Other astronomers soon measure parallaxes for additional stars. The first rungs of a cosmic distance ladder begin taking shape. Now brightness can be interpreted more carefully. A star may appear faint because it is intrinsically dim, because it is extremely distant, or because material lies between you and it. Separating those possibilities becomes essential for understanding galactic structure. Photography adds another revolution. Human eyes become tired. Photographic plates do not. Leave a plate exposed beneath a telescope, and faint light can accumulate over time. Objects too dim for immediate human vision gradually leave chemical traces. The smell of photographic chemicals enters astronomy. Observatories acquire darkrooms. Glass plates fill cabinets. Night skies become permanent records rather than fleeting views remembered in notebooks. This changes the study of the Milky Way profoundly. Astronomers can compare images taken years apart. They can catalogue enormous numbers of stars and examine faint nebulae with increasing detail. Photography also exposes the beauty of structures invisible to casual observation. Dark lanes cut through crowded star fields. Glowing clouds surround young stars. Clusters emerge from regions that once looked nearly empty. Still, interpretation remains difficult. One 19th-century argument concerns the nature of nebulae. Some astronomers suspect that many are unresolved groups of stars. Others believe at least some consist of luminous gas. Spectroscopy provides a way forward. In 1864, William Huggins examines the spectrum of a planetary nebula and finds bright emission lines rather than the continuous stellar spectrum he expected. Some nebulae really are glowing gas. Others display stellar spectra. The word nebula has been hiding several fundamentally different objects beneath one convenient label. A cloudy appearance can mean many things. Some objects are gas within the Milky Way. Some are star clusters, and some spiral nebulae will eventually prove to be entire galaxies far beyond it. That final distinction remains unresolved. Astronomers continue debating the size of the Milky Way and the status of spiral nebulae. Meanwhile, spectroscopy begins organizing stars themselves. At Harvard College Observatory, large collections of stellar spectra are classified systematically. Women working as astronomical computers perform much of this painstaking analysis. Williamina Fleming, Antonia Maury, and Annie Jump Cannon become central figures in this work. Cannon eventually develops the spectral classification sequence that becomes familiar as O, B, A, F, G, K, and M. The order looks slightly peculiar because earlier classification systems were reorganized as stellar physics improved. Astronomy kept the letters. Science occasionally leaves historical clutter in the filing cabinet. The Sun belongs to Class G. You now know it is neither uniquely hot nor uniquely large. It is one star among an enormous population with varied temperatures, masses, colors, and lifetimes. Another Harvard astronomer, Henrietta Swan Leavitt, will soon uncover a relationship that transforms cosmic distance measurement. While studying variable stars, she notices that certain stars change brightness according to a pattern connected with their true luminosity. That discovery belongs more fully to the next stage of your journey. For now, pause beneath the 19th century Milky Way. The band overhead still looks familiar to ordinary eyes. Yet inside observatories, it has changed completely. Stars now possess chemical compositions. They have measurable motions. Some have geometric distances. Their light reveals temperature and physical conditions. Photographs preserve them. Spectra dissect them. Researchers still disagree about how large the Milky Way truly is, where its center lies, and whether the spiral nebulae belong inside it. But the questions are becoming testable. The galaxy is no longer merely being counted, it is being analyzed. Soon, variable stars, globular clusters, and the troublesome darkness of interstellar dust will finally push the Sun away from the center of the Milky Way. Humanity has already lost the center of the planetary system. Now it is about to lose the center of the galaxy as well. By the opening decades of the 20th century, the Milky Way had become a measurable collection of stars. Spectroscopy revealed their chemistry, photography preserved their light, and parallax provided reliable distances to the nearest stellar neighbors. Yet the galaxy's overall shape remained surprisingly uncertain. You can imagine yourself entering an observatory around 1915. The dome smells of machine oil, cold metal, and old wood. Outside, wind brushes against the building while photographic equipment waits beneath the open slit. The Milky Way crosses the darkness overhead. Somewhere behind its bright clouds lies the Galactic Center. Astronomers do not yet agree where. Earlier star counts had often placed the Sun relatively close to the middle. This conclusion seemed reasonable because visible stars appeared distributed around us in ways that suggested no enormous displacement. But the galaxy had hidden an important piece of evidence. Dust. Interstellar dust absorbs and scatters visible starlight, making distant regions appear dimmer than they truly are. Dark lanes visible within the Milky Way are not necessarily empty gaps. They are curtains. This misunderstanding distorted maps for generations. If you count only what visible light allows you to see, the galaxy can appear smaller and more centered upon the Sun than it actually is. Another clue comes from globular clusters. These ancient collections contain hundreds of thousands, sometimes millions, of stars packed into roughly spherical systems. Harlow Shapley begins studying their distribution. His reasoning is wonderfully indirect. If globular clusters surround the Milky Way, their arrangement might reveal the galaxy's true center even when dust obscures much of the stellar disk. But distances are required. Here, variable stars become crucial. Henrietta Swan Leavitt had studied Cepheid variables in the Magellanic Clouds and discovered that their pulsation periods were related to their luminosities. Longer period Cepheids were intrinsically brighter, once calibrated. This relationship provides astronomers with a powerful distance tool. Measure how quickly a Cepheid varies. Infer its true brightness. Compare that with how faint it appears. Distance follows. It is an elegant method. A star that repeatedly brightens and fades becomes a marker placed across enormous space. Using variable stars and other assumptions, Shapley estimates distances to globular clusters and maps their distribution. The result displaces humanity again. The clusters gather around a region far from the Sun, toward the constellation Sagittarius. The solar system is not near the galactic center. You live in the outskirts. Modern measurements place the Sun roughly 26,000 light-years from the center of the Milky Way, embedded within its disk. Shapley's exact size estimates were too large, partly because interstellar extinction and calibration problems remained incompletely understood. Still, his central insight was transformative. The galaxy has a center. You are not in it. There is something almost soothing about humanity's repeated astronomical demotions. Earth loses the center of the planetary system, and the Sun later loses the center of the Milky Way. The universe keeps refusing to arrange itself around us. Yet another major disagreement remains. How large is the Milky Way compared with the entire universe? Some astronomers argue that the Milky Way constitutes essentially the whole stellar universe. Spiral nebulae would therefore belong inside it. Others suspect those spirals are separate stellar systems at immense distances. The disagreement becomes famous through the Great Debate of 1920. Harlow Shapley and Heber Curtis present contrasting views at the Smithsonian Museum of Natural History in Washington. The event is sometimes remembered as a dramatic showdown. Reality was quieter. It was a scholarly exchange concerning several astronomical problems, and neither participant held the fully modern answer on every issue. Shapley favored an enormous Milky Way and generally placed spiral nebulae within it. Curtis argued for a smaller galaxy and supported the island universe interpretation of spirals. Both had evidence. Both had difficulties. One strange piece of evidence involved reported observations suggesting rapid rotation within spiral nebulae. If those objects were distant galaxies, the implied physical speeds would become implausibly enormous. Those measurements later proved unreliable. Scientific debates can be redirected by bad data. Another puzzle involved novae, stars that suddenly brightened dramatically. Some appeared within Andromeda and other spiral nebulae. Their apparent faintness could support enormous distances, but interpretation remained uncertain. Then the observational situation changed. A more powerful telescope was already watching the sky from California. The 100-inch Hooker telescope at Mount Wilson Observatory collected far more light than earlier instruments. Its mirror opened a deeper universe. Before that discovery arrives, however, Astronomers must understand something else about the Milky Way's shape. It is flattened. The dense concentration of stars along the luminous band strongly suggests that most visible galactic stars occupy a disk-like structure. Globular clusters extend much farther above and below that disk, forming part of a broader halo. The disk itself contains gas and dust. Young stars often gather near its plane. Older populations can occupy different distributions. Astronomers begin realizing that the galaxy is not one uniform swarm. It has components. The idea of spiral structure also develops gradually. From inside the disk, spiral arms are frustratingly difficult to trace. Dust blocks distant visible light, while our embedded viewpoint makes broad patterns hard to reconstruct. Imagine trying to map a spiral city while standing inside one crowded street. You see buildings nearby. The overall design remains hidden. Later radio astronomy will solve much of this problem by observing wavelengths capable of penetrating dust. For now, optical astronomers work with incomplete views. Researchers also continue debating exactly how early 20th century observations should be interpreted because distance scales were repeatedly revised. Measurements that seemed secure could shift as calibration improved. That uncertainty is not a weakness. It is part of the process. Every new distance measurement redraws the map. Stand outside the observatory again. The air feels colder now, and the Milky Way appears almost three-dimensional once you know that dark regions contain hidden stars. Toward Sagittarius lies the center. You cannot see it clearly with your eyes. Dust prevents that. Yet beyond those dark clouds, stellar density rises enormously around a central bulge. At the very heart sits an object nobody in 1920 understands. A supermassive black hole waits there. Its mass is roughly 4 million times that of the Sun. Humanity will discover its presence only after new kinds of astronomy learn to see beyond visible light. First, however, the Milky Way must lose one final claim to cosmic importance. It is not the universe. Soon, a faint variable star in the Andromeda Nebula will reveal a distance too enormous to fit comfortably inside our galaxy. The pale smudge known since ancient times is about to become another galaxy. And when that happens, the universe will expand almost overnight. In October 1923, Edwin Hubble examined a photographic plate taken through the 100-inch Hooker telescope at Mount Wilson Observatory in California. On the plate was the faint spiral glow of Andromeda, already familiar to generations of astronomers. Inside it, Hubble identified a variable star. That tiny changing point would help enlarge the known universe beyond the Milky Way. Imagine yourself on Mount Wilson during one of those observing nights. The mountain air is cool and dry, while machinery murmurs softly beneath the great telescope dome. You smell oil, metal, and pine drifting from the darkness outside, above Los Angeles. The sky is still much darker than it will become during later decades. The Hooker telescope gathers light with a mirror 100 inches across. Compared with Galileo's narrow instrument, it is almost absurdly powerful. Yet the principle remains familiar. Gather more light, see farther. Hubble had been searching for novae within the Andromeda Nebula. On one photographic plate, he initially marked several candidates before realizing that one object changed brightness like a Cepheid variable. Cepheids had become crucial because of Henrietta Swan-Leavitt's earlier discovery. Their pulsation periods reveal their intrinsic luminosities. If you know how bright a star truly is, and compare that with its apparent brightness, you can estimate its distance. Andromeda suddenly possessed a measuring marker. The result was devastating for the idea that every spiral nebula belonged inside the Milky Way. Hubble's original distance estimate was smaller than today's value because the Cepheid calibration remained imperfect. Even so, Andromeda was clearly far beyond the accepted dimensions of our galaxy. The island universes were real. The Milky Way became one galaxy among many. That conceptual change is difficult to reproduce today because you already grow up hearing about billions of galaxies. To astronomers of the early 20th century, the scale of the transformation was enormous. The universe had not physically expanded overnight. Human awareness had. Other spiral nebulae could now be understood as distant galaxies containing their own stars, gas, dust, and histories. Some were viewed face-on. Others appeared as thin streaks because their disks were seen edge-on. The Milky Way itself belonged to this family. You could never photograph it from outside. Of course, you were trapped inside the subject. Astronomers therefore began comparing external galaxies with measurements of our own to infer structures hidden by perspective and dust. The word galaxy gained its modern cosmic meaning. Our Milky Way was no longer synonymous with the entire stellar universe. Then Hubble helped reveal another surprise. Working with observations of galaxies and measurements of their spectral shifts, he found a relationship between distance and recession velocity. More distant galaxies generally showed larger redshifts. Georges Lemaitre had already connected expanding universe solutions of Einstein's relativity with observational evidence and derived a distance-velocity relationship. The emerging conclusion was extraordinary. The universe itself was expanding. This did not mean galaxies were simply exploding outward from one ordinary point into pre-existing empty space. On sufficiently large scales, space itself evolves. The distances between widely separated, gravitationally unbound galaxies increase with time. The Milky Way does not expand internally with the universe in the same simple way. Its stars are gravitationally bound. Gravity holds the galactic system together, while cosmic expansion dominates across much larger distances. You can feel how strange this is. Newton had given astronomers a universe governed by universal gravity. Einstein had transformed gravity into the geometry of space-time. Now observations suggested that space-time itself possessed a cosmic history. Einstein's general theory of relativity, published in 1915, had already changed the conceptual foundation beneath astronomy. Matter and energy influence the geometry of space-time. That geometry influences motion. Gravity is therefore not merely an invisible pulling force traveling across an otherwise passive stage. The stage participates. Einstein initially introduced a cosmological constant into his equations while seeking a static universe. Later, historical retellings often claim he called this his greatest blunder after cosmic expansion was discovered. The famous quotation is poorly documented. Astronomical history enjoys polishing a good line. The deeper point is more interesting. Even brilliant scientists carry expectations into their equations. Observation decides which expectations survive. During the decades following Hubble's work, astronomers refined the cosmic distance scale. They discovered that Cepheid variables came in different populations with different luminosity relationships. Distances changed. The universe grew older and larger, but the fundamental conclusion remained. Galaxies exist beyond the Milky Way. Meanwhile, our own galaxy became increasingly difficult to understand, precisely because we lived inside it. Optical telescopes struggled to see through the dusty galactic plane. Visible light from the central regions was heavily absorbed. A new window was needed. Radio astronomy provided it. In 1931, Karl Jansky was investigating sources of radio interference for Bell Telephone Laboratories. His unusual rotating antenna looked more like industrial machinery than a traditional observatory. It became known informally as Jansky's merry-go-round. He detected persistent radio noise. The source shifted with sidereal time rather than ordinary solar time, indicating that it came from beyond Earth. Jansky traced the strongest emission toward the constellation Sagittarius. He had detected radio waves from the Milky Way. The galaxy had become audible to instruments. Not literally audible in space, of course. Radio signals could be converted into forms humans could analyze, allowing invisible radiation to reveal structures hidden from optical telescopes. Grote Reber soon built a radio telescope in his Illinois backyard and mapped radio emission across the sky. His dish looked wonderfully out of place among ordinary homes. Yet it helped establish radio astronomy as a serious observational field. After the Second World War, radio techniques developed rapidly. One particularly useful signal came from neutral hydrogen. Hydrogen atoms can emit radio radiation at a wavelength of about 21 centimeters under specific conditions. This radiation passes through much of the interstellar dust that blocks visible light. Astronomers could finally trace gas across large portions of the galactic disk. The hidden Milky Way began emerging. Radio observations revealed concentrations of hydrogen associated with spiral structure. The galaxy increasingly appeared as a barred spiral system, though details would continue changing with better measurements. The Sun occupied no special location. It traveled around the Galactic Center with billions of neighboring stars. One orbit takes roughly a few 100 million years. Since the Sun formed about 4.6 billion years ago, it has completed only a few dozen galactic circuits. Dinosaurs lived on Earth during a different portion of the Sun's galactic journey. The continents changed, species appeared and vanished. The solar system continued quietly around the Milky Way. Astronomers were now learning to map that journey using forms of light invisible to human eyes. Yet radio astronomy would reveal something stranger near the galactic center. Sagittarius contained an unusually compact and powerful radio source. Later generations would call it Sagittarius a star. Something massive was hiding there. The Milky Way had surrendered its place as the entire universe. Now humanity was ready to discover that its own galaxy contained an invisible heart. By the middle of the 20th century, the Milky Way had become visible in ways no human eye could experience directly. Radio receivers detected cold hydrogen through dust, while spectroscopy measured motions hidden inside apparently motionless points of light. The galaxy was becoming stranger. Imagine yourself beside a radio telescope after midnight. The enormous dish moves slowly against the stars, accompanied by motors and the quiet hum of electronics. Cold metal carries the smell of moisture, while cables disappear into rooms filled with instruments. You look upward. Your eyes see darkness toward much of the galactic center. The receiver does not. Radio waves pass through regions that visible light struggles to penetrate, revealing gas, magnetic activity, stellar remnants, and energetic objects throughout the Milky Way. In 1974, astronomers Bruce Ballack and Robert Brown identified an exceptionally compact radio source near the exact center of our galaxy. It became known as Sagittarius A star. The source itself was intriguing, but the surrounding region offered an even more important clue. Stars were moving extremely fast. During later decades, astronomers used increasingly powerful infrared telescopes to watch individual stars near the galactic center. Infrared radiation passes through dust more effectively than visible light, opening a clearer view of this crowded region. The stars traced remarkable paths. Some swung around an apparently empty point. One especially useful star, commonly called S2, completes an orbit in roughly 16 years. By following its motion, astronomers could estimate the mass concentrated inside its orbit. The answer was extraordinary. Something containing about 4 million times the mass of the Sun occupied a region small enough that the most convincing explanation was a supermassive black hole. The Milky Way had a dark heart. Black holes themselves emerged from the strange logic of relativity. Einstein's general theory described gravity as curved space-time, and solutions to his equations allowed regions where gravity became so intense that an event horizon formed. Beyond that boundary, light could not escape. For decades, many physicists wondered whether such objects existed in nature or merely represented mathematical curiosities. The sky eventually answered. Stellar mass black holes could form when sufficiently massive stars ended their lives and collapsed. Supermassive black holes occupied the centers of many large galaxies. How the earliest massive black holes formed remains uncertain. Astronomers still investigate whether they began from remnants of early stars, collapsing gas clouds, dense stellar systems, or several pathways working together. Sagittarius, a star, is comparatively quiet today. It does not consume matter at anything approaching the dramatic rates seen around active galactic nuclei elsewhere. That calm is fortunate. The center of the Milky Way is already lively enough. Gas clouds, massive stars, magnetic fields, and stellar remnants crowd the surrounding region. A black hole is not a cosmic vacuum cleaner, roaming around, swallowing everything nearby. Objects can orbit it safely if they remain sufficiently distant, just as planets orbit the Sun. Gravity behaves normally outside the immediate extreme environment. If the Sun were somehow replaced by a black hole with exactly the same mass, Earth's orbit would remain almost unchanged. Sunlight would become a rather serious issue, but gravity would not suddenly drag Earth inward. While astronomers investigated black holes, another invisible mystery was spreading across galactic astronomy. Stars near the outer parts of spiral galaxies were moving too quickly. If most galactic mass came from visible stars and gas concentrated toward the center, orbital speeds should decline substantially at large distances. Observations did not show the expected pattern. Rotation curves often remained unexpectedly flat. One major figure in establishing this evidence was Vera Rubin, working with Kent Ford and others during the 1960s and 1970s. Their measurements strengthened the case that galaxies contain much more mass than visible matter alone can explain. The idea of unseen galactic matter was older. In the 1930s, Fritz Zwicky had inferred missing mass within the Coma galaxy cluster. Jan Oort had also investigated stellar motions near the Sun for evidence concerning unseen matter. But accumulating galactic rotation measurements made the problem increasingly difficult to ignore. Something invisible appears to surround galaxies. Today, this component is called dark matter. In the standard cosmological picture, the Milky Way sits within a vast dark matter halo, extending far beyond the bright stellar disk. You cannot smell it. You cannot touch it directly. It emits no ordinary light that telescopes can simply photograph. Its presence is inferred primarily through gravitational effects. And despite decades of experiments, the fundamental particle nature of dark matter remains unknown. Researchers continue testing alternative explanations and possible modifications of gravitational theory. Although dark matter remains central to the prevailing cosmological model, the visible Milky Way is therefore only part of the galaxy. Most of its gravitational mass appears to be invisible. This realization changes how you picture the night sky. The glowing band overhead looks like the galaxy. It is really the luminous portion embedded within a much larger gravitational structure. Meanwhile, another discovery introduces an entirely different kind of celestial object. In 1967, Jocelyn Bell Burnell noticed unusual repeating radio signals while examining data from a radio telescope. The pulses were astonishingly regular. For a brief period, the possibility of artificial origin was considered playfully enough that one signal acquired a nickname referring to little green men. The explanation proved nearly as remarkable. Pulsars are rapidly rotating neutron stars. A neutron star forms when the core of a sufficiently massive star collapses, compressing roughly stellar mass into an object only tens of kilometers across. Its magnetic field can produce beams of radiation. As the star rotates, those beams sweep through space. When one crosses Earth, your telescope detects a pulse. The Milky Way was filling with stellar corpses. White dwarfs, neutron stars, and black holes revealed that stars possess life cycles. They are born from gas. They shine. They change. They die. Some return in rich material to interstellar space, where later generations of stars and planets can form. The galaxy is therefore not merely rotating. It is recycling. Elements forged inside stars become ingredients for new systems. Carbon, oxygen, silicon, iron, and many other elements essential to rocky planets and living organisms have histories connected with stellar processes. You are part of that recycling. The calcium in your bones and iron carried through your blood were assembled through cosmic processes long before Earth existed. The Milky Way is not merely your location. It is part of your ancestry. By the late 20th century, astronomers could observe this galactic ecosystem across radio, infrared, visible, ultraviolet, X-ray, and gamma-ray wavelengths. Each window revealed a different Milky Way. Then astronomy acquired another messenger. In 2015, detectors measured gravitational waves from merging black holes, ripples in space-time predicted by relativity a century earlier. The universe could now be studied without relying only upon electromagnetic radiation. Humanity had moved from naked eyes to instruments capable of sensing space-time itself. Yet these discoveries raised a deeper question. How did a galaxy containing dark matter, black holes, ancient stars, gas clouds, planets, and eventually observers come into existence? To answer that, you must finally leave recorded human history behind. You must travel backward more than 13 billion years, toward the young universe where the first pieces of the Milky Way were beginning to gather. Travel backward more than 13 billion years, and almost everything familiar disappears. There is no Earth beneath your feet, no sun warming your face, and no Milky Way crossing a dark sky. There are not even mature galaxies resembling the graceful spirals photographed by modern telescopes. The universe itself is young. You cannot truly stand here. There is no safe ground, breathable air, or quiet hillside from which to watch events unfold. Still, imagine floating beyond danger while the early cosmos slowly changes around you. There would be no sound traveling through empty space. No smell reaches you. There is only radiation, matter, gravity, and enormous stretches of darkness gradually becoming structured. The story begins much earlier than the Milky Way, about 13.8 billion years ago. The observable universe existed in an extremely hot and dense state. Space expanded and cooled, allowing increasingly complex forms of matter to emerge. This was not an explosion from one location into surrounding emptiness. Expansion occurred throughout space. During the first minutes, conditions allowed the formation of simple atomic nuclei, especially hydrogen and helium nuclei, with small quantities of other light elements. Atoms themselves came later. For hundreds of thousands of years, the universe remained hot enough that free electrons scattered light repeatedly. Then temperatures fell sufficiently for electrons and nuclei to combine into neutral atoms. Light could travel much more freely. That ancient radiation still surrounds you today. It is called the cosmic microwave background. Its discovery in 1965 by Arno Penzias and Robert Wilson provided powerful evidence for a hot, early universe. Curiously, they were not initially searching for the origin of the cosmos. They were investigating persistent microwave noise. After eliminating possible sources, including material left by pigeons inside their antenna, the unwanted signal remained. Sometimes cosmology arrives accompanied by inconvenient birds. The cosmic microwave background is extraordinarily uniform, but it contains tiny variations. Those slight differences matter enormously. They reflect small density variations in the early universe, regions containing slightly more or less matter than average. Gravity begins amplifying them. Matter attracts matter. Denser regions gather additional material and become still denser. Over immense periods, this slow gravitational growth produces the foundations of galaxies. Dark matter plays a central role in the standard picture. Because it does not interact with light like ordinary matter, dark matter could begin forming gravitational structures under conditions where ordinary gas remained strongly influenced by radiation. Vast dark matter concentrations gradually developed. Ordinary hydrogen and helium fell into their gravitational wells. Somewhere within this cosmic web, the ancestry of the Milky Way began. There was no single morning when the galaxy suddenly switched on. Its formation was a process. Many smaller structures formed, collided, merged, and exchanged material. Gas accumulated within growing dark matter halos. Dense regions cooled. Gravity compressed them further. Eventually, the first generations of stars appeared. Exactly when the first stars formed remains an active area of research. Current evidence and simulations place their emergence within the universe's first few 100 million years, though important details remain uncertain. These first stars were chemically primitive. The early universe contained overwhelmingly hydrogen and helium, with only traces of a few lighter elements. Carbon, oxygen, silicon, and iron were largely absent. Stars would manufacture them inside stellar cores. Nuclear fusion converts lighter elements into heavier ones while releasing energy. Massive stars can build increasingly heavy nuclei through successive stages of fusion. When some massive stars end their lives explosively, they scatter newly produced elements into surrounding space. The universe becomes chemically richer. Later stars form from that enriched material. Astronomers describe this enrichment using the language of stellar populations and metallicity. In astronomical terminology, elements heavier than helium are broadly called metals. Chemists may quietly object. Astronomers continue anyway. Some extremely old stars survive today within the Milky Way's halo and ancient clusters. Their chemical compositions act like archaeological evidence. A star containing very few heavy elements likely formed from material enriched by relatively few previous stellar generations. You can therefore read history inside starlight. Modern astronomers search for exceptionally metal-poor stars because they preserve clues about conditions in the early galaxy. They are not necessarily the absolute first stars. Those primordial stars were probably massive enough that few, if any, survive today. Instead, ancient low-mass stars may contain material influenced by those earliest stellar explosions. They are fossils made of plasma. Meanwhile, the young Milky Way grows through mergers. Small proto-galactic systems fall together under gravity. Their stars and gas become incorporated into a larger structure. This process is not gentle. Galaxies can distort one another through tidal forces. Gas clouds collide and compress, sometimes triggering intense periods of star formation. Yet individual stars rarely collide directly. Galaxies contain enormous empty spaces between stars. Two stellar systems can pass through one another, while most stars avoid physical impacts. Gravity performs the larger rearrangement. The early Milky Way probably experienced several important mergers. Modern surveys have identified stellar populations whose motions and chemistry suggest origins in smaller galaxies consumed long ago. One prominent ancient merger is associated with a system commonly called Gaia Enceladus. Its debris appears to survive among stars, moving through the Milky Way's halo. Names change as evidence develops, and researchers continue debating the exact histories, masses, and timing of several proposed merger events. Galactic archaeology remains a young science. You reconstruct collisions from stars that survived them billions of years later. Imagine finding pieces of several ancient cities scattered through one modern landscape, then determining which stones belong together by their composition and motion. That is roughly the challenge. Gradually, the Milky Way develops a more organized rotating structure. Gas with angular momentum settles increasingly into a disk. Stars form within this material. Earlier populations contribute to the halo and central regions, while later generations help build the evolving disk. The process does not follow one perfectly clean sequence. Real galaxies are untidy. Gas flows inward. Material is expelled by stellar explosions. Satellite galaxies arrive. Star formation rises and falls. The central black hole grows. The disk can be heated, disturbed, and rebuilt. Researchers still debate important details concerning exactly when the Milky Way's thin and thick disks emerged and how particular merger events shaped them. Better stellar ages continually refine the story. Yet by billions of years after the universe began, something increasingly recognizable has appeared. A large galaxy now rotates within a massive dark matter halo. Its stars contain more heavy elements than the earliest generations. Its gas has been enriched by repeated stellar deaths. Within that enriched material, chemistry unavailable to the primordial universe has become common. Carbon exists, oxygen exists, iron exists, silicon exists. The ingredients for rocky planets are accumulating. The Milky Way has spent billions of years preparing material that will eventually become a rather ordinary yellow star and a small planet around it. The galaxy does not know this. There is no destination written into its evolution. But about 4.6 billion years ago, inside one region of its disk, a cloud of enriched gas and dust will collapse. A new star will ignite. Around it, leftover material will assemble into planets. One of those worlds will eventually produce creatures capable of looking back through 13 billion years of galactic history. The Milky Way has built its ancient foundations. Now it is ready to build the galaxy you recognize. About 4.6 billion years ago, somewhere inside the Milky Way's rotating disk, an ordinary cloud began collapsing. There was no audience, no human watched the cloud darken, and no astronomer recorded the first gathering of material. The galaxy had already existed for billions of years before this small event began. Imagine approaching the cloud from a safe distance. It is cold by terrestrial standards, composed mainly of molecular hydrogen, with helium, dust, and traces of heavier elements mixed throughout. There is no breathable atmosphere. There is no sound carried through the surrounding vacuum. Yet, if you could touch one of its dust grains, you would be touching material with an astonishing ancestry. Earlier generations of stars had helped create many of its heavier elements. Some massive stars produced elements through fusion and scattered enriched material when they died. Other stellar explosions and compact object events contributed additional elements through different processes. The cloud is recycled galaxy. Gravity draws portions of it together. One region becomes increasingly dense until a protostar develops near its center. Material falls inward, while angular momentum causes surrounding matter to flatten into a rotating disk. The young sun is forming. Around it, dust grains collide and stick. Small particles become larger aggregates. Aggregates become planetesimals, and some planetesimals grow into planetary embryos. The process is messy. Objects collide. Orbits change. Material is scattered. Eventually, the familiar solar system emerges from this crowded construction site. Earth forms roughly 4.5 billion years ago. Its ingredients belong to the Milky Way's long chemical history. The iron, eventually concentrated inside Earth's core, was unavailable in meaningful abundance during the universe's earliest moments. Neither were the silicon-rich minerals beneath your feet. The oxygen you breathe has a cosmic ancestry extending through generations of stellar nucleosynthesis. Although Earth's atmosphere later acquires much of its free oxygen through life, you live on assembled galactic debris. It is a surprisingly dignified form of recycling. The Sun itself is not particularly unusual. It is a middle-aged G-type main-sequence star, one among enormous numbers of stars distributed across the Milky Way. Its location is also comfortably unremarkable. The solar system lies roughly 26,000 light-years from the Galactic Center, within the disk, near a smaller spiral feature commonly called the Orion Spur, or local arm region. The Milky Way's full spiral structure is harder to map than photographs of other galaxies might suggest. You remain inside the disk. Dust blocks distant visible light, and overlapping structures complicate the view. Modern evidence indicates that the Milky Way is a barred spiral galaxy. A central bar of stars stretches across the inner region, while major spiral arms and smaller structures wind through the disk. Exactly how many prominent arms should be emphasized depends partly on what traces astronomers use. Young stars, molecular clouds, hydrogen gas, and masses can highlight somewhat different patterns. Researchers continue refining the geometry. Spiral arms are also not simply rigid collections of stars moving together forever like painted stripes on a wheel. Their behavior is more complicated. Different theories describe spiral patterns through density waves, gravitational instabilities, transient structures, and interactions within the disk. The precise nature and longevity of the Milky Way's spiral features remain subjects of active study. What is certain is that spiral regions contain abundant gas and many sites of star formation. Enter one of those stellar nurseries, and the galaxy changes character. Cold molecular clouds stretch across light years. Dense pockets collapse under gravity. Young stars ignite inside dusty cocoons. Some become massive blue stars that burn through their nuclear fuel quickly. Others form as smaller, cooler stars capable of surviving for tens or even hundreds of billions of years. The Milky Way manufactures stars at a modest rate today. That rate has changed throughout galactic history. The young galaxy likely experienced periods of more vigorous star formation, while mergers and changing gas supplies altered activity over billions of years. Every generation modifies the next. Stars return material through winds and stellar deaths. Gas becomes chemically enriched. New stars inherit that material. Planets become increasingly possible around stars containing heavier elements, although planetary systems can form across a surprisingly broad range of stellar compositions. By the time the Sun appears, the galaxy has become chemically mature enough to provide abundant rocky material. Meanwhile, the Milky Way continues consuming smaller companions. Satellite galaxies orbit within its gravitational environment. The large and small Magellanic Clouds are among the most prominent companions visible from Earth's southern hemisphere. Their relationship with the Milky Way is dynamic. Gas extends around and between these systems in enormous structures shaped by gravity and interaction. Smaller dwarf galaxies also orbit our galaxy. Some are being torn apart. The Sagittarius dwarf spheroidal galaxy provides a striking example as it travels around the Milky Way. Tidal forces strip away stars. Those stars form streams wrapping through the galactic halo. The galaxy is still assembling itself. Not dramatically enough for you to notice while drinking tea beneath the stars, but unmistakably on astronomical timescales. The halo contains many such archaeological clues. Stellar streams preserve the paths of disrupted systems. Ancient globular clusters carry information about early star formation. Chemical compositions identify stars that may share common origins. Astronomers increasingly combine these clues with precise stellar motions. The result is galactic archaeology. Instead of digging through soil, you excavate phase space. You measure where stars are, how quickly they move, which direction they travel, and what elements their atmospheres contain. From those clues, vanished galaxies can sometimes be reconstructed. Historians of the Milky Way therefore work with evidence scattered across the entire sky. Some details remain uncertain. Researchers debate which ancient mergers contributed most strongly to particular stellar populations and how much they altered the developing disk. Even the chronology of the central bar remains under investigation. Galactic history refuses to become perfectly tidy, yet the broad picture is clear. The modern Milky Way contains several overlapping structures. A thin disk hosts much of the ongoing star formation. A thicker stellar component contains generally older populations. A central bulge and bar dominate the inner galaxy. Globular clusters and ancient stars populate a much larger halo. Dark matter extends farther still. At the center waits Sagittarius A star. Around all of this, the galaxy rotates. The Sun travels around the center at hundreds of kilometers per second. One galactic orbit takes roughly 200 million years, or somewhat longer, depending on how the journey is defined. You feel none of this motion. Your chair remains still. Your room does not tremble. Yet while you listen, Earth circles the Sun. The Sun travels through the galaxy, and the Milky Way moves within the local group. Everything is moving inside something larger. For billions of years, this evolving galactic environment has carried the solar system with it. Life appears on Earth. Complex organisms eventually develop. Humans arrive extremely late. Then, after almost the entire history of the Milky Way has already passed, one species begins building instruments capable of reconstructing what happened before it existed. The galaxy created the elements. The elements helped create observers. And now, those observers are beginning to map the Milky Way star by star. By the beginning of the 21st century, astronomers faced a strange problem. Humanity understood that the Milky Way was a barred spiral galaxy containing hundreds of billions of stars. Yet our position inside its dusty disk still prevented us from seeing its complete structure directly. The solution was to measure almost everything possible. Imagine yourself inside a modern observatory control room. There is no need to press your eye against a cold telescope. Computer screens glow softly. Ventilation murmurs, and electronics add the faint smell of warm plastic. Outside, an enormous instrument follows the sky automatically. Elsewhere, telescopes orbit above Earth's atmosphere. Astronomy has become a planetary network of detectors. Some instruments collect visible light, others observe infrared, ultraviolet, radio, X-rays, or gamma rays. Each wavelength reveals a different layer of the Milky Way. Infrared astronomy is especially valuable inside our dusty galaxy. Longer wavelengths penetrate many clouds that hide distant stars from visible light telescopes. Look toward the Galactic Center with your eyes, and dust blocks much of the view. Observe in infrared, and crowded stellar fields emerge. Radio astronomy penetrates the disk differently. Neutral hydrogen traces large-scale gas, while molecular emissions reveal cold clouds where future stars are forming. Mesas provide exceptionally precise measurements of some star-forming regions. Together, these observations help reconstruct spiral structure from the inside. Then comes Gaia. Launched by the European Space Agency in 2013, the Gaia spacecraft begins one of the most ambitious mapping projects in astronomical history. Its task sounds deceptively simple: measure stars. Again, William Herschel would recognize the basic ambition. Although the scale would seem almost supernatural, Gaia repeatedly observes enormous numbers of stars, measuring positions, parallaxes, proper motions, brightnesses, and other properties with extraordinary precision. Instead of counting stars through one eyepiece, astronomers now build a multidimensional map containing more than 1 billion stellar sources. You can watch the galaxy move. Some stars travel with the disk. Others follow unusual paths through the halo. Groups share motions suggesting common origins. Streams reveal dwarf galaxies torn apart long ago. The Milky Way's past survives in velocity. Gaia data help identify signatures associated with ancient merger events, including the population linked with Gaia Enceladus. Astronomers compare motion with chemical composition to reconstruct when different populations entered or formed within the galaxy. This is archaeology without ruins. The ruins are stars. Yet even Gaia cannot see everything. Dust obscures some regions, while extremely faint objects remain difficult to measure. Distance uncertainties increase for more remote stars. Researchers therefore combine surveys. Infrared missions reveal hidden populations. Ground-based spectroscopy measures stellar chemistry. Radio observations trace gas. X-ray telescopes identify violent systems containing compact objects. No single instrument owns the Milky Way. Modern astronomy works by assembling incomplete views. The galaxy also contains planets in astonishing abundance. In 1995, astronomers announced the discovery of a planet orbiting a sun-like star outside our solar system. Many earlier exoplanet discoveries and candidates had involved unusual systems, including planets around a pulsar. Soon, the number of known worlds grew rapidly. NASA's Kepler Space Telescope transformed the field by monitoring stellar brightness and searching for tiny repeated dips caused when planets crossed their stars. The result changed expectations. Planets are common. Small planets are common. Systems can contain worlds packed into orbits unlike anything in our solar system. Some planets circle extremely close to their stars. Others travel around two stars. Some worlds appear to wander without a known host star. The Milky Way is full of planetary experiments. Exactly how many potentially habitable worlds exist remains uncertain because habitability depends on far more than size and orbital distance. Atmospheres matter. Stellar activity matters. Geology, chemistry, magnetic environments, and long-term climate stability may matter. Still, the basic conclusion is difficult to avoid. Our galaxy contains an enormous number of planets. That returns you to one of humanity's oldest questions. Are you alone? Modern searches for extraterrestrial life approach this question in several ways. Astronomers study planetary atmospheres for chemical combinations that might indicate biological processes. Radio surveys search for possible technological signals. Researchers investigate icy moons, Mars, and other nearby environments for evidence of past or present life. Nothing has yet provided confirmed evidence of extraterrestrial life. The silence remains. Some interpret that silence through the famous Fermi paradox, the tension between potentially numerous habitable environments and the absence of obvious technological civilizations. There are many proposed explanations. Perhaps intelligent life is rare. Perhaps technological societies do not last long. Perhaps communication across interstellar distances is exceptionally difficult. Perhaps we are searching incorrectly. Or perhaps the galaxy contains more life than we realize, quietly separated by distance and time. No answer has been demonstrated. The Milky Way also speaks through messengers other than light. In 2015, the first direct detection of gravitational waves opened another observational window. The signal came from merging black holes more than 1 billion light-years away, beyond our galaxy. But gravitational wave astronomy also reveals compact object populations connected with stellar evolution across the universe. Future detectors may provide richer information about sources within the Milky Way. Neutrinos offer another messenger. These elusive particles pass through enormous amounts of matter with little interaction. Detectors buried underground or embedded within Antarctic ice search for them. Astronomy is becoming increasingly multisensory, although the senses belong to machines. One especially memorable modern achievement arrives in 2022. The Event Horizon Telescope collaboration releases an image of Sagittarius A star, the supermassive black hole at the center of the Milky Way. The image does not show the black hole itself. A black hole emits no ordinary light from within its event horizon. Instead, you see glowing material surrounding a central dark region shaped by extreme gravity. Humanity has effectively photographed the environment around the invisible heart of its own galaxy. Think about the distance traveled intellectually. Ancient observers saw the Milky Way as a luminous path. Galileo resolved it into stars. Herschel counted those stars. Shapley displaced the sun from the center. Radio astronomers penetrated the dust. Modern instruments now watch stars orbit a central black hole. Yet enormous mysteries remain. Dark matter still lacks an identified fundamental particle. The exact history of the Milky Way's earliest assembly remains incomplete. The spiral arms continue to be refined. The census of faint stars, rogue planets, stellar remnants, and small satellite galaxies is unfinished. Even the total mass of the Milky Way remains uncertain. That uncertainty is not surprising. You are attempting to weigh a galaxy while living inside it. Step outside tonight, however, and none of this complexity announces itself. You hear ordinary nighttime sounds. Cool air touches your skin. Perhaps distant lights hide most of the Milky Way completely, but above that glow, the galaxy continues rotating. Billions of stars move through an invisible dark matter halo. Planets circle many of them. A black hole waits at the center, and human instruments continue listening. The Milky Way has finally become measurable in motion, chemistry, gravity, and time. Now only one direction remains: forward. The same physics that reconstructed the galaxy's past can also offer glimpses of what happens after the present sky is gone. About 4 billion years from now, the night sky above Earth, if anyone remains to see it, will begin looking profoundly unfamiliar. Andromeda will no longer be a faint smudge. It will dominate the heavens. Today, the Andromeda galaxy lies roughly 2.5 million light-years away and is approaching the Milky Way overall. Measurements of its motion allow astronomers to model what may happen across the distant future. The details remain uncertain. Current models suggest that a close encounter or merger is possible several billion years from now, although improved measurements continue refining the predicted trajectory. Imagine watching the approach from a safe world. The air is cool against your skin. Night insects make their familiar sounds, while the ground releases the faint smell of evening moisture. Above you, Andromeda stretches across an enormous portion of the sky. Its stars do not rush toward you like sparks. Galactic encounters unfold slowly. Hundreds of millions of years pass between stages that a cinematic animation might compress into seconds. Gravity begins reshaping both galaxies. Their stellar disks stretch and distort. Long tidal structures can form as stars are pulled into new trajectories. Gas clouds respond more dramatically because gas can collide, compress, and produce bursts of star formation. Individual stars, however, are separated by enormous distances. Even when galaxies overlap, direct collisions between stars remain extremely unlikely. The encounter sounds violent. For most stars, it is mainly gravitational choreography. The solar system could be moved into a different galactic orbit. It might end up farther from the remnant's center or follow a substantially altered path. Predictions vary because tiny differences in initial conditions matter across billions of years. There is another complication. The Sun itself is aging. Long before the ultimate fate of the combined galaxies becomes relevant to Earth, the Sun's increasing luminosity will transform our planet. In roughly 5 billion years, the Sun will exhaust hydrogen in its central core and evolve toward the red giant stage. Its outer layers will expand enormously. Earth's precise fate during this period depends on competing processes involving solar mass loss and tidal interactions. Whether the planet is ultimately engulfed remains a subject requiring detailed modeling. Habitability will disappear much earlier. The familiar Earth is temporary. So is the familiar Milky Way. If the Milky Way and Andromeda eventually merge, the resulting system may resemble a more rounded galaxy rather than today's two separate spirals. The central supermassive black holes could eventually form a binary and later merge. Such a merger would release powerful gravitational waves. There is a curious symmetry here. Humanity began studying the heavens with naked eyes. Our descendants, if they exist, might study galactic transformations through vibrations in space-time itself. Yet the future of the Milky Way is larger than one encounter. The galaxy currently forms new stars from cold gas. That supply is not unlimited. Some gas becomes locked inside long-lived stars and stellar remnants. Some returns through stellar winds and stellar deaths. Material can also enter or leave the galaxy over enormous timescales. However, star formation will decline. The bright blue stars disappear first because they consume their fuel quickly. Sun-like stars survive much longer. Smaller red dwarfs can endure for extraordinary spans, potentially trillions of years. The future galaxy gradually reddens. Its brilliant stellar nurseries fade. The glowing clouds associated with young, massive stars become increasingly rare. The universe grows quieter. There is no literal silence to increase, because interstellar space does not carry ordinary sound as air does. But visually, the change feels like silence. New lights appear less frequently. Old lights linger. Eventually, stars exhaust their nuclear fuel. Sun-like stars leave white dwarfs. More massive stars can leave neutron stars or black holes after much shorter lives. Low-mass stars follow slower paths. The galaxy fills increasingly with remnants. White dwarfs cool. Neutron stars fade. Black holes remain. Planets may continue orbiting dim stellar corpses or surviving low-mass stars. Some objects can be thrown into interstellar space through gravitational encounters. The galaxy becomes darker on still longer timescales. Gravitational interactions gradually rearrange stellar orbits. Encounters can eject some stars, while others migrate toward denser regions. The exact evolution depends upon the structure of the future galactic remnant. At these scales, certainty becomes softer. Astronomers can apply known physical laws, but predictions depend upon processes that unfold across times far beyond direct observation. There are also deeper uncertainties. Proton decay has never been observed. If protons eventually decay, ordinary matter has one kind of distant future. If they remain stable indefinitely, another future follows. The behavior of dark matter across immense timescales also depends upon its still unknown nature. Dark energy creates an even broader mystery. Observations show that cosmic expansion is accelerating. The simplest successful description treats dark energy as a cosmological constant, but its fundamental nature remains unknown. If its behavior remains approximately constant, distant gravitationally unbound galaxies will eventually recede beyond practical observation. The local group's merged descendants could become increasingly isolated. Future observers might inhabit a universe where evidence for the wider cosmos is much harder to obtain. Imagine that strange astronomy. A civilization arising unimaginably far in the future might look upward and see primarily the stars gravitationally bound to its own galactic remnant. Most other galaxies could have disappeared beyond its observable horizon. The universe would still exist. Evidence of its larger structure would simply be more difficult to recover. Your own era is therefore special in one modest sense. You live when ancient radiation remains observable, distant galaxies remain visible, stars are abundant, and cosmic expansion can be measured across enormous distances. You can reconstruct both beginning and future. That brings you back to the first night of this journey. Imagine again the prehistoric observer standing beneath the Milky Way. There are no equations. There is no telescope. The observer sees only a pale band and countless stars. Yet the same galaxy already contains the ingredients from which future astronomers will emerge. Billions of years of stellar evolution have created carbon, oxygen, iron, and other elements incorporated into planets and living bodies. Eventually, human eyes turn upward. Babylonian scholars record planetary movements. Egyptian observers connect celestial cycles with calendars and seasons. Greek thinkers build geometrical models. Medieval astronomers measure and correct inherited tables. Copernicus moves Earth. Kepler abandons perfect circles. Galileo opens the Milky Way with glass. Newton connects falling objects with orbiting worlds. Herschel counts stars. Spectroscopy reads their chemistry. Shapley moves the Sun away from the Galactic Center. Hubble moves the Milky Way away from the center of the universe. Radio telescopes penetrate dust. Space observatories map billions of stars. Detectors hear space-time tremble. And all of this happens during the smallest fraction of the galaxy's life. The Milky Way is more than 13 billion years of accumulated change. You arrive near the end of that immense history, at least so far. Yet you can look backward. That may be the most remarkable part. A species formed from material recycled through the galaxy has learned to measure the age, structure, motion, and ancestry of the system that created its world. You are not outside the cosmic story. You are one brief expression of it. The iron in your body belongs to ancient stellar history. The ground beneath you formed from material assembled inside the Milky Way. Even the eyes looking upward are galactic products. And now the night becomes quiet again. The instruments can rest. The observatory dome closes slowly, and the faint hum of machinery disappears into darkness. Above you, stars continue their patient movement around the Galactic Center. The Milky Way needs no audience. It turns through the darkness as it has for billions of years, carrying old stars, newborn worlds, quiet dust clouds, and the memory of galaxies absorbed long ago. You can let those distances soften now. Let the spiral arms drift beyond thought, and let the ancient starlight continue without needing to follow it. The galaxy keeps moving, the universe keeps expanding, and beneath one ordinary star, on one small world, you can simply rest.